Hi, I'm Bjorn Turius, and this is part 7 of my video series on process control. In previous videos, we have seen how a simple feedback controller can reduce disturbances to the process. We found that the controller is the most effective when the gain is high, but we have also seen that there's a limit to the magnitude of the controller gain that the loop can tolerate before it starts self-oscillating. In a previous video, we found the ultimate gain, applied it to a gain-only controller, and made changes to the set point. In this video, we'll also make set point changes, but with controller gains well below the ultimate gain, and see where this lands us. We set up the controller for feedback control, a dead time with 0.1 hours and 50% level. We try gain equal to 2.3, which is the inverse of the process gain. We make a set point change from 50 to 60 degrees. For some reason, the tank temperature levels out at 55 degrees, not 60. A minute's reflection reveals why. Had the tank temperature somehow remained at 50 during the adjustment, the error would have remained at 10 degrees and the output from the heater would have been 70. The heated stream combined with the disturbance stream at 50 would have made the tank at 60, but the tank does not remain at 50 under feedback control. When it has climbed up to 55 degrees, for example, the error is only 5 degrees and the heater exit is 60. The average of 50 from the disturbance stream and 60 from the heated stream is of course 55, and that's where the tank is going to remain. How can we fix this? What we would like to do is to reset the bias term in the control equation so it produces enough output to the heater to keep the tank at set point without error. There is an automated way of doing this, and it's called integral action. This action keeps the bias term changing by integrating the error until the error is 0. Let's see how this works in the simulation by putting in a value of 0.4 hours for the integral time in what now is a PI controller. The controller now gets the tank temperature set point, but it takes a long time. Let's see if we can speed it up by using a shorter integral time of 0.2 hours. And now we'll go in the opposite direction down to 50 degrees. Yes, that went faster. We had a little bit of what's called overshoot, where the tank temperature actually went below 50 degrees, the set point, but then leveled out at 50 degrees, which is good. Let's see if we can improve the response even more by decreasing the integral time. I set it to 0.05 hours, which is 3 minutes, and I'm going to test another set point change. So that's not very promising. There's obviously a limit for how low the integral time can be before we start running into self-oscillations. We now have two parameters in a PI controller that can be used to achieve optimal performance in a control loop. Both of these have limits to their values for the loop to remain stable. How do we select the right values for the two parameters? This opens up a major topic of loop tuning. We'll look in detail on some of the more popular methods in future videos.